Okay, let's just carry on with this. All right, so we were looking at the last section in section 1.5, and we were just almost finishing the last example there where we were trying to solve the homogeneous linear system. So we solved the inhomogeneous linear system where we said AX equals to what? B, where B is not equals to, it's not equals to 0. Where B is not equals to 0. So here, what we got is P naught plus V or RU plus SV, whereby R and S are elements of real number, equals to P naught plus the span of U and V, the span of U and V. Now, if it is homogeneous, then it means AX equals to 0 vector. Means AX equals to 0 vector. So what we need to solve, like the example that we did, is we need to solve x1 minus 2x2 plus 5x3 equals to 0, minus 3x1 plus 6x2 minus 15x3 also equals to 0. So that is what we need to solve. So this is for homogeneous linear system. Homogeneous linear system. So we write this now in augmented matrix form. So the solution is now 1, -2, 5, and 0, -3, 6, -15, and 0, Now, since we reduced this previously, where there was some values of B here, so what we got is actually almost similar to this. So it is what we get when we reduce this. That means it is R2 is R2 plus 3R1. R2 plus 3R1. What we get is 1, -2, 5, and 0, and then 0, 0, 0, and then 0. So that is what we get. That is what we get. Now, here, so we have our basic variable, which is, so we have our basic variable, which is x1, and our free variables are x2 and x3. Our free variables are x2 and x3. So we say, free variables, that is where we don't have the pivot solution. So we don't have the pivot solution. It just stands. So that if you don't have the pivot solution, then those will give us the variables, free variables. So x1 is the basic and x2 are the free variables. So our new linear system here will now be x1 minus 2x2 plus 5x3 equals to 0. So then our x1 will now be equals to, you take the others to the other side, minus 2x2 plus, so this is plus actually, and then minus 5x3, minus 5x3. Now our solution set will now be equals to x, which is equals to x1, x2, x3, is now equals to 2x2 minus 5x3. Yeah. And our x2 is our basic x2. And our x3 is also our basic variable. Our free variable, I mean x3. So when we write this one now in parametric vector form, then what we get is now 2. So basically we factor, so we write this as 2x2, x2 here, and then 0 for x3, okay? Plus the one for x3 is here, minus 5x3, and then 0 for x2, and then x3 there, and then x3. So when we now factor out the variable there, so x2 will now be 2, 1, and 0, and then plus x3 will now be 5, 0, and 1. 5, 0, and 1. So we can let this one to be our vector u, and this one to be our vector v. So in this case, then therefore we can write this as su plus ru or tu, tv, where s and t are elements of real number, is similar to the span of u and v. Is similar to the span of the vector c. Vector c. Where our u is equals to this vector, which is 2, 1, and 0, and our v is equals to this vector, 5, 0, and 1. So what can we see from here? Now we can see that the inhomogeneous linear system is associated now with what? The homogeneous linear system. The homogeneous. So for the inhomogeneous, then we well, the values of b were not 0, right? So what we got here, p was not 0. So it could have been, we had now our p plus the span of that. Okay. Now this will lead us to a theorem. This theorem 3. Uh, 2.2. This is a theorem. If P naught is a solution of the matrix AX equals to B, AX equals to B, then the solution sets of AX equals to B is P naught plus V for all V is any solution of the homogeneous matrix equation. AX equals to 0. AX equals to 0. Now we remember when we did this one, AX equals to B. Our solution was P naught plus the vector, right? Now, when we have done now the homogeneous linear system, then our solution is just the V, where V is any solution of the homogeneous matrix equation AX equals to 0. For the homogeneous This is what? These are zero. For the inhomogeneous, then it is plus what? The vectors. And for those vectors. Yes. Any question after that? Okay, that one is the end of section 1.5. Now we're going to do section 1.7. Section 1.7. 1.7. And this is linear independence of vectors. This is actually the application of homogeneous linear system. So in this section, what you're going to look at, section 1, is the linear independence and dependence of vectors. Okay, so what is linear independence and linear dependence? So let's look at 1.1, which is definition. If we let V1, V2, all the way to Vp be vectors in vector space Rn, then A, the vector V1 up to Vp are linearly independent if x1 v1 plus x2 v2 plus xp vp only equals to 0 vector, equals to 0 vector, equals to 0 vector. That is, it is homogeneous, equals to 0 vector. Yeah. Only has non-trivial, only has trivial solution. Only has trivial solutions. So trivial solutions. So for it to be have trivial solutions, then that means all the column vectors have what type of positions, right? We don't have the free variables. We don't have the free variables as trivial solutions. Number B, the vectors V1, V2, all the way to Vp are linearly dependent if x1 v1 plus xp vp equals to 0 has non-trivial solutions. So now, if we have the free variables, then it now becomes linearly dependent. If we don't have the free variables, then it becomes what? We get the trivial solution. So they are linearly independent. Number C. Now, if it is linearly dependent, then it comes now to, we need to get the solution now. So that solution is where we get this C. If the vector V1 all the way to Vp are linearly dependent, then there are not all none or not all 0 numbers P1 all the way to CP, such that C1 of V1 plus C2 V2 plus CP VP equals to 0, which is called a linear relation of V1, V2, all the way to VP. Now, if we find that it is linearly dependent, then we now continue solving it, and then we now get the values of C1, C2, C3. So this is now what we call the linear relation. The linear relation. The linear relation. Okay, now let's look at example number 1. Let's look at the first example here. Determine whether the vectors are linearly dependent or linearly independent given vectors are linearly dependent, then find a linear relation of them. So determine whether the vectors are linearly dependent, and if it is linearly dependent, then find the linear relation. So if we have these vectors, number A, 1 minus 3 is 0, minus 3, 7, and 1, 3, negative 1, negative 4, and then negative 2, 2, and 3. We have those vectors here. Now determine whether this is linearly dependent or linearly independent. So in this case, solution. So what we need to do is we can denote, we can say denotes V1, V2, V3, and V4. So we can denote these ones as V1, V2, V3, and V4. V1, V2, V3, and then we can say determine whether x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 is equals to what? Is equals to 0 vector. Only has trivial solution or has non-trivial solutions. Please do not forget this. Only has trivial solutions or has non-trivial. Only has trivial solutions or non-trivial solutions. So in this case, then we need to now write this in augmented matrix form: 1, -3, 0, and then -3, 7, and 1, and then 3, -1, -4, and then -2, 2, and 3, and then now 0, 0, and 0 there. And then now we do what? We reduce it. Then we reduce. So to reduce now this matrix, then R2, our new R2 will be R2 plus 3 R1. R2 plus 3 R1. So what we get is 1, negative 3, 3, negative 2, 0. And then we have 0, negative 2, 8, negative 4, and 0. And then 0, 1, negative 4, 3, and 0. So that is what we get in the first one. Then we can now multiply the second row by. So our new second row, which is R2, can now be multiplied by 1 over 2 R2. 1 over 2 R2. So what we get is now 1, negative 3, 3, negative 2, 0, then 0, 1, 4, 2, and then 0, and then 0, 1, negative 4, 3, and 0. Oh, yeah. So this is negative. Then we now get the new R3, which is R3 minus R2. Again, if you, I insisted on this, some of you are making some little mistakes in the exam. So if you're getting the new R2, then it should be, yeah, R2. R2 should also be R2. Okay. And then now we manipulate the other. So basically, here, our R2, which is this, our new R2, will now be our R2, which is this one, plus now we now start manipulating the R1, which is multiplied by 3. So R2 should be R2. Look at this again, R2 again, R2. And then here, R3 also R3. So do not interchange. If you do so, then you might make some mistakes. So again, also, when you're trying to manipulate now R2, then you try to simplify also. So you see there is something that is common there, then you can simplify easily. Okay, now R3 there, so we subtract, so 1, negative 3, 3, negative 2, 0, then 0, 1, negative 4, 2, and then 0, and then finally, this one is 0, 0, and then 0, 1, and 0, 0, and 0. So what can we see from there? So here we have our basic variable. We have our basic variable here. Do we have our basic variable here? No, right? So we have our basic variable there. So this is x1, x2, x3, x4. Now our basic variable will now be x1, x2, and what? And x4. And our free variable will now be x3. Our free variable is where we don't have a pivot position. So now, since we have those ones there, then it means this is what? Linearly. If we have our free variable, then it means it is what? Linearly dependent. So it is linearly dependent. So it is linearly dependent. So we can say, since x3 is a free variable. The homogeneous vector equation has non-trivial solutions. Non-trivial solutions. So we have non-trivial solutions. So the given vectors are linearly dependent. Linearly dependent. So now, when now it is now linearly dependent, then we now need to get a solution. So when it is now linearly dependent, then we now need to get a linear relation here. So we now need to get a solution here. Now to get a solution here, then we now need to reduce this one. So now to reduce that completely. So we have gotten so what we've gotten is 1, -3, 3, -2, and 0. And then we have 0, 1, -4, 2, and 0. And then 0, 0, 0, 1, and 0. So that is what we have there. So we now need to get the solution of this. We now need to get the solution of that. So to get a solution, since this is our basic variable, this is our basic variable, and this is our basic variable, then we need to make the ones which are above the basic variables to be what? Zeros, to be zeros, starting from this. So here, so our new R2 will now be R2 minus 2 R3. And then also to get our new R3, R1, then it is R1 plus 2 R, R3. R1 plus 2 R3. So what we get there is 1, -3, 3, and then 0, 0, 0, 1, -4, then 0, 0, and then 0, 0, 0, 1, and 0. So this is also our basic variable. So we need to make this one to be what? 0. So here it will now be, to get our new R1, then it is R1 plus 3 R2. So it is 1, 0, and -9, 0, 0, and then 0, 1, -4, 0, 0, and then 0, 0, 0, 1, and 0. So that is what we get. So our basic variable is x1, x2, and x4. Our free variable is x3. So our new linear system here will now be 1, which is x1 minus 9x3 equals to 0. And then x2 minus 4x3 equals to 0. And then our x4 equals to 0. Our x4 equals to 0.
Get the position above basic variables. Zero. You need to do that without the whole row. So you have 0, 1, -4, 2, 0. Then go to 0, 0 again. But you didn't look up the other numbers. Is that okay to do, or you have to do it the whole row?
You need to do it to the whole row because when we multiply, so when we say R2, we want to get a new R2 here, right? So it is this R2 here minus 2R minus 2R3. Okay. So it is still, this is still the same because 2 by 0 is 0. 2 by 0 is 0. So 1 minus this one is 0. 2 by 0 is 0. So the only one which is subtracted is okay. Yeah. All right. So this is our new linear system. So we take these values to the other side. So x1 equals to 9x3, x2 equals to 4x3, and x4 is still the same, which is 0. So our solution set will now be equals to x, which is equals to x1, x2, x3, and x4, which is now equals to x1 is 9x3, x2 is 4, x3, x3 is our free variable, and then x4 is what? x4 is 0. x4 is 0. So finally, this is the same as so it means that this is like x3 is 9, 4, 1, and then 0. 9, 4, 1, and 0. For what? For any x3. For any x3. Now, if we let x3 to be 1, if we let x3 to be equals to 1, then x1 equals to 9, x2 equals to 4, x3 equals to 1, yeah, and then x4 is equals to 0. x4 is equals to 0. So therefore, our new linear relation now. So our linear relation. So these are basically our C1. Sorry, this is C3. This is our C1. This is our C2, and this is our C4. So now, to get the new linear relation, which is C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times C4 equals to 0. And this V1, V2, V3, V4 are the vectors which we had. So finally, this is the same as C1 is what? 9, and our vector was what? Was 1, -3, and 0. Plus C2 here is 4, and our vector is -3, 7, and 1. Plus our C3 is 1, and our vector is 3, -1, and -4. And then finally, plus C4, which is 0, and our vector is -2, 2, and 3, equals to 0. Equals to 0. So that is our linear relation. That there. Any question after that? So this is our vector that we got. And this is our solution, C1. So you can actually write this one as 9V1 plus 4v2 plus v3 equals to 0, since the other one is what? 0.
Is C4 is
Any question up to that? Okay, another example. Let me solve. So let's solve this one a little faster. Number B, if we have this 0, 0, 2, and then 0, 5, -8, and -3, 4, and 1. Check whether this is a linear independent or dependent. So you do the same thing. So you want to look at x1, b1, plus x2, b2, plus x3, b3, equals to what? Equals to 0 vector. Equals to 0 vector. So you write this in augmented matrix form, 0, 0, -3, and then 0, 5, 4, 0, and then 2, -8, 1, and 0 there. 1 and 0. So to solve this, to reduce this, then you need to switch. So that to reduce that, so you need to switch R1 and what? R3. So when you switch, then we have 2 - 8, 1, 0, 0, 5, 4, 0, and then 0, 0, -3, and 0. So looking at this is already what? Reduced, right? This is already reduced. So we have our basic variable, basic variable, basic variable. So what is this? This is what? Linearly. So this, since we don't have, so since all variables are basic, then homogeneous vector equation only has the trivial solutions. Only has trivial solutions. Okay, now we can meet on to continue from there. So I was busy over the weekend grading your exams. I haven't graded your homework, so I will have time to grade them. Okay, I'll post the solution of your exam in Moodle. If you have any issues, I always have my office hours, or you can email me anytime you want. No, you can.